This is part 2 of lesson 10.5, the alternating series. In the second part of the lesson, we're going to talk about some error bounding of alternating series, and we're also going to talk about the difference between a alternating series that converges absolutely and one that converges conditionally. So what we can do for some alternating series, as long as they're convergent, is we can talk about a partial sum as a way to approximate the actual sum of the series. So then when we do that, we create an error, and this error is the remainder, where it's defined in the following way, where Rn is the remainder, and it's the difference between the actual sum and the partial sum that we are using. So if a convergent alternating series satisfies the conditions that a sub n plus 1 is less than or equal to a sub n, then the absolute value of the remainder involved in approximating the sum is less than or equal to the first unused term. So in other words, the absolute value of this difference is always going to be less than or equal to the next term that you're not using. So we have our three conditions for having a convergent series. It's alternating, decreasing in magnitude, and it has a limit of 0. If those are met, then what we can do is approximate that sum using an nth partial sum. And our error will be always bounded by the absolute value of the first truncated term. So in other words, if you're going to approximate with the first 100 terms, that sum, then the 101st term will be the boundedness of the error. Okay, so let's work through some of this. Maybe it'll make a little more sense. So I started this a little bit. So if a series is alternating converges absolutely, and we'll talk more about that in a little bit, then the sum of the series can be approximated by adding the values of the terms with an error of the absolute value of the first unused term. So we are using negative 1 to the n plus 1 times 1 over n squared, which we know is a convergent alternating series. We did that earlier in the other lesson. So what we're going to find is when we, if you notice here, we have the first 10 terms, 1, 2, 3, 4, 5, 6, 7, 8, 9, I can't count, the first 9 terms, and that is the sum. So the first unused term is going to be negative 1 to the 10 plus 1 over 10 squared, and so that would be negative 1 over 100. So that's where this number comes from. Therefore, the error is going to be less than the absolute value of that term. So it's going to be less than 0.1. So now what we're supposed to do is find the sum of the first 200 terms, and then for the error, we're going to find the 201st term. So on your calculator, in case you haven't done this for a while, if you have an 84, what you're going to do this is you're going to go under second stat, you're going to go over to math, and you're going to choose number 5 sum. Then you're going to do again second stat, and you're going to choose ops, and you're going to choose number 5 sequence. And then I already have it entered in here. So you're going to put negative 1 raised to the n. Well, you can use whatever variable. I just use the variable key. The x plus 1, and make sure that's in parentheses for the power, and then divided by x squared. Our variable's x. We're starting at 1. We're going to end at 200, and we're counting each term. So we're going to step through that. So I'm going to enter through this as if I entered it from scratch. I'm going to hit paste, and it's going to put it on my screen, and then I hit enter, so I'm going to get the answer. So the answer is going to be 0.8225. So let's write that on our notes. So the first 200 terms is going to be 0.8225. And now what is the error? So what we're going to do to find the error is we're going to take the absolute value, so our R sub n, the absolute value of that, has to be less than or equal to the absolute value of negative 1 to the 200 plus 1 over I'm sorry, that should be 201 because that's the n we're on. 201 plus 1 over 201 squared. And when we do that, we get a value of 0.000248. So that's pretty accurate using just the first 200 terms. All right, just real quick now, to show the sum on the Inspire, what you're going to do is you're going to go to your symbol palette, and I already have it highlighted there. You're going to use the summation. It's already set up for you. And then you're going to, now here you can use n directly because you have the variable. So n from 1 to 200. And then in parentheses, I'm going to make a fraction just to make my life easier. I'm going to put -1. I'm going to raise that to the n plus 1 power. And then in the denominator, I'm going to put my n squared. And it's a lot easier. So I hit enter, and there's the answer. All right, let's do a couple of examples here. So given this series, which is -1 to the n minus 1 over n factorial, we are first to approximate the sum s of the series by using the first 4 terms. So we can just write those out since it's the first 4 terms. So s is going to be approximately equal to, if I put 1 in, I get 1, and then minus 1 over 2 factorial, which is 2, plus 1 over 3 factorial, which is 6, minus 1 over 4 factorial, so I'm just going to take the 6 and multiply that times 4, so I get 24. And when I add those together, I get 0.625. Now I'm being asked to explain why the estimate in Part A differs from the actual value by less than 100. So what I'm really looking for is what is the boundedness of the remainder. So I'm looking at the absolute value of the remainder. So what I'm going to say that is my error, because that's what it's saying. We're looking for our error. So we want to see that we're going to call this R4, and that is going to be equal to our actual S minus our S4. And remember, we have that it has to be less than the 5th term. So then we can say that, so our error has to be less than our A5, and our A5 is going to be positive 1 over 5 factorial, which is going to be 1 over 1/20th. And that is definitely less than 100th. So then we're supposed to use our results to explain why S cannot equal 0.7, knowing all this. Well, remember that our actual sum, if we take S4 and subtract off S5, that is always going to be less than our sum. So that means our actual S4, which was 0.625, plus our A5, we're going to be somewhere in between there. So if we take our S, it's going to be somewhere in between those two boundaries. So we have 0.625 minus our 1/20th, and that's got to be less than our sum, but our sum has got to be less than 0.625 plus 1/20th. And when we do that, our numbers are going to be in decimal form. 0.61667 is less than S, and this is still bounded by a number that is smaller than 0.7. So S cannot equal 0.7. And finally, what is the difference between absolute and conditional convergence? So we can classify series in several ways. One, divergent. The second one is absolutely convergent. And if it's absolutely convergent, We know this because the absolute value of the series is convergent. If a series is absolutely convergent, then we know it's just convergent. And it's conditionally convergent if the series itself is convergent, but the absolute value is not convergent. So I'm going to show you how that works. The first example is an example of a conditionally convergent series. So here's what we know for letter A. We're going to take the absolute value of our S sub n, and that's going to equal 1 over n. And we know that this is a divergent harmonic series. We've used that a lot. We know 1 over n is divergent. But here's what we do know, though. If we go through our terms, because our conditions, we know this is an alternating series from that part. We can see that our nth term is greater than 0, that it is decreasing because the terms are going to get smaller as we go, because we go 1, a half, a third, okay? And we also know that if we take the limit of our nth term, that is going to go to 0. So it meets the conditions for a convergent alternating series. So it's just not absolutely convergent because the absolute value of it does not converge. So therefore, we can say that the series that we're given here is conditionally convergent. All right, so let's look at another one. So if we look at the next one, if you're asked to determine if it's absolutely convergent, conditionally convergent, the first thing you should do is check for absolute convergence. Because if it's absolutely convergent, you're done. That's all you have to do. You don't have to do anything else like we did with part A. So at part B, the first thing I'm going to do is I'm going to look at this series. Having a little trouble with my pen again today, like I did the last one. So this is just going to give me a convergent P series, because I can now just ignore the -1, the alternating part, because they'll make every term positive. And this is, of course, a convergent P series. So since the absolute value converges, I can say, therefore, my given alternating series converges absolutely. All right, next example. If you want, it might be easier to write this in terms of a fraction to see what you're looking at here. Now, if you notice something special about this, if we take the absolute value of this, and again, I'm checking for absolute convergence first, because if it converges absolutely, it is going to converge altogether. So I can think of this as a convergent geometric series. So this is now a geometric series with an r less than 1. So this is convergent. So I can say that my series, since the absolute value converges, converges absolutely. And our last example, this one is written a little differently, but if you think about what's going to happen with this cosine of pi n, the values at 1, this will be cosine of negative pi, that'll be at negative 1, and then the next n would be 2 pi would be positive 1, then again 3 pi would be negative 1. So this is another way to write an alternating series. So don't let that throw you just because it has the cosine there. It is still an alternating series, so it's just written in terms of cosine. So we're going to look at the absolute value of this series to see if it converges absolutely first. If it doesn't, then we'll have to use our alternating series test to see if it converges conditionally. But hopefully you notice already that we really have the same thing that we had in part B. We end up with 1 over n squared, a convergent p-series. So what we can say is, since the absolute value converges, our original series, our alternating series, is absolutely convergent, so converges absolutely. So that is the end of our discussion on alternating series. If you have any questions, please feel free to ask them. And in our next video, we're going to talk about some different types of series.